About 11 months ago, I decided that it would be a nice idea to have some of the distinguished scientists around, and I should say in some sense still around, who were actual participants and creators during the early years, the formative years of quantum mechanics during the 20s and 30s. During the last IAP, Professor Weisskopf from here gave two delightful talks, really, as he called it, on my life as a physicist, but his life as a physicist encompassed such a large range of the formative years and creators of quantum mechanics that it really was a personal reminiscence history. And at that time I also had asked Professor Bethe if he could come down and give such a talk, and he was otherwise occupied last year, but he wrote and asked after 11 months if he, since he was going to be at MIT at this time, if he could now give such a talk. And it's my pleasure to say that it's been arranged. This is kind of a second-order introduction because I'm just going to let Professor Weisskopf do the proper introduction of Professor Bethe. So, Professor Weisskopf, if you will.
Well, first of all, I would like to express my own, and I'm sure your appreciation, to Ted Dukas. He single-handedly organizes these events, these happenings, I should say. And I think it's a wonderful thing for MIT, for physics, and for our human relations, that there is a man, Ted Dukas, who thinks of this, and I hope he will do it many times more. Of course, you might run out of people, but until but until you run out of people, I hope you do as well as you did, and thank you all. But let's give him Now, why should I introduce Hans Bethe? Everybody knows who Hans Bethe is, so what should I say? But I'm supposed to say something. So maybe I should tell the story which some of you know, because I think I even published it somewhere, namely my first, or almost first encounter with Bethe. I was at that time an assistant of Pauli, and we did some nice calculations about the quantum field theory of scalar particles, which at that time were not yet known to exist, and I was supposed to calculate the pair creation of those particles, and in a pair creation by gamma rays, and everybody knew, of course, at that time also that Bethe and Heitler indeed have calculated these things for the real particles, for electron and positrons. At that time, real particles. They're still real particles. But we've got others too now. And so I went to him and said, tell me, how do you do this? What techniques did you use? And Hans, in his usual clarity and simplicity, explained to me how to do it. And it was, at that time, a pretty difficult calculation. So I asked him, how long will it take for me to do this? Well, then he said, well, I would take about 3 days. You will take 3 weeks. And now let me right away say that it did take me 3 weeks, indeed, and I did it wrong at the end. And then, well, that was my first encounter, at least my first serious encounter with Hans. I saw him at meetings, and then, however, very soon afterwards, both of us came to this country, and he, as you know, came to Cornell, and I came to Rochester, two places that are only 90 miles apart from each other, and then started a wonderful personal collaboration and personal relation, which I value infinitely much, and which certainly coined my own life as a physicist. And these were the days when nuclear structure physics began, and then later on the days when the renormalization theory of electromagnetic field theory was born, lamp shift, etc. And the days are these days and weeks and discussions of collaboration were just quite essential for me, and I hope a little of a pleasure for Hans also. And so I would thank him for all this and for so much more, because then afterwards our friendship grew and became deeper and deeper, and it was not only how to calculate an integral, but how to face as a physicist, or let me see, as a human being, the world which we have to face, in which he helped us and me so very much. And this was one of the most important things that happened in these post-war days, where Hans was our leader, and Hans was the man whom we always looked for, the reasonable, serious, sometimes humorous advice. You know, that mixture is necessary. Niels Bohr once said that there are things that are so serious that you can only joke about them. And therefore, sometimes one has to use humor, and Hans has that humor. Now let me, before I let Hans talk, I know you are all waiting for him, but I would like to say one word which is very near to my heart. There's one danger about the series that Ted Dukas is organizing. And the danger is that you think that physics was so wonderful at that time and is so dreary and boring today. This is not true. There's nothing of this kind. Of course, it is true that the years of 23, 24, 25, 26 were extremely exciting. And a new idea, namely quantum mechanics, came up. But quantum mechanics is a great idea, and it didn't come up, well, it was invented at that time, of course, but we didn't really understand it. I'm not even sure whether we understand it today. And that's what I mean, this goes on, and I think every one of you had and should have that pleasure of insight, what I like to call the joy of insight, at the moment when he understood it. I'm not saying when he has been taught, because that's not the same thing. When he understood it, when he got the insight of how wonderful how deeper into the mechanism of nature we were looking through quantum mechanics. This you have today and ever. In addition to this, of course, all the development of quantum mechanics, I'm sure we'll hear from Hans, are based on a lot of dreary work, in fact more dreary than some of the work now, which happened before or during the time of quantum mechanics. I remind you of spectroscopy, of the analysis of every single atom, and that one understood it only half, only quarter, and only vague ideas, etc. And so physics is just as interesting, in fact, in some respect, more interesting today, because today we live perhaps not in an explanatory age like at that time, but in an exploratory age. And what comes up today in almost all fields of physics, laser physics, low temperature physics, plasma physics, astrophysics, special new nuclear physics, and of course particle physics, all these new phenomena, new worlds that are opened today due to the development of technology since then, are so fantastically exciting just because we don't understand them yet, that anybody who gets the impression, and I hope you won't get the impression, that physics was wonderful today and dreary, wonderful at that time, and dreary today, is simply wrong. It was wonderful and dreary at that time and now. And now, one more remark. You must have heard me many times say we shouldn't be specialists in a small field of physics. We should be generalists. And I tried all my life to be generalist. That means I tried, to understand nothing about everything instead of everything about nothing. And now, let me say, one thing I have learned in my many, many decades with Hans Bethe. He is really, but truly, a man who understands everything about everything. Hans.
Dr. Dukas, Vicky, and friends of MIT. Thank you very much for this wonderful introduction. I am not quite sure whether it's me you were talking about. And one of the things I was very fortunate about, I must say, is that after this rather inauspicious first meeting with the 3 days and the 3 weeks, we became such good friends. I must make a small disclaimer. I was not present at the creation. I was not present at the birth of quantum mechanics. It was created in 1925-26, and I really became aware of it only in 26 when it was a very lusty infant, but completely born. My story will be mainly a personal story, namely my relation to the early quantum mechanics. I graduated from high school in 1924 and went to the University of Frankfurt, which was not a very good university at the time. In particular, nobody there really understood quantum theory as it then existed. It was being talked about in a mysterious way. The professor of theoretical physics, Madelung, who was a good theorist, obviously did know some quantum theory, but the main impression that his students got was that this was something which nobody could possibly understand. The old quantum theory, which started with Bohr's theory of the hydrogen atom in 1913, had a lot of successes early in its life. It explained not only the hydrogen atom, but also its fine structure. Then the X-ray spectra, a great success of the theory, band spectra of molecules, and the periodic system. There was a little bit of swindle in the theory of the periodic system, but we let that go. But in the 2 first years of my studies, 1924 and 25, it really was a very confused system. Nothing would work. There were contradictions everywhere. And some people lost hope. At my University of Frankfurt, I got the main stimulation not from the professor of theoretical physics, but from the associate professor of physics. There was only one professor and one associate professor in physics. The associate professor was first Gerlach of the Stern-Gerlach experiment, and later Meissner, a very good spectroscopist who is not very well known. No, that was a different Meissner, who was in Munich. Meissner was particularly kind to me. He said, well, Frankfurt is not a place for you. You should go to a place where you can really learn theoretical physics. And the best place was Munich. In Munich was Sommerfeld, who had been the teacher of the best of the young theoretical physicists, especially Pauli and Heisenberg, who had previously been the teacher of also quite excellent theorists like Ewald and especially Debye, and who had a school visited by most of the young theorists to be. Sommerfeld had written a book called Atombau und Spektrallinien, which summarized all the successes of the old quantum theory, and which I read only while I was studying there. I should have read it before I got there, but that's all right. Anyway, he accepted me in his seminar, which was somewhat unusual. I had 2 years of study behind me, but you should remember that in Germany at that time, and I think even today in most European countries, high school graduation meant far more than it does here. For instance, I had a working knowledge of calculus when I left high school. And the first years of college are concentrated on subjects of your specialty, so that after 2 years you might be considered ready for graduate study. Sommerfeld's seminar was most fortunate in the year 1926, because Schrödinger's papers on wave mechanics were just coming out, and Sommerfeld, being a big shot, got all the Galilei proofs of Schrödinger's papers as soon as they came from the press. And so the Galilei proofs were available for the members of his seminar. Every member had to take one part of the 5 papers by Schrödinger, not one whole paper, but a fraction of it, and had to report on it. It took, I think, all semester to get through it. And this was a very good thing, because everything was done most carefully. Sommerfeld would not stand any sloppiness. If there was anything sloppy, he would ask some very stupid questions. And everybody was aware that this was an extremely stupid question, but it brought out that the student or other person really hadn't understood the paper and now had to explain it much better. It was a further advantage for me that I did not know the old quantum theory, because if I had known that, then I would constantly have searched for connections between the old quantum theory and wave mechanics. And as it was, this was a new subject and a new theory which explained everything people wanted to know. Sommerfeld also was very helpful, because he told us the polynomial method to solve differential equations, to solve, for instance, the wave equation for the radial wave equation for the hydrogen atom, which is a far easier method than most which were in the literature, and made it clear that the solution was not difficult. Differential equations were Sommerfeld's great love. He was at home with them and had been for about 30 years of his working life. He had written books about them, and in particular he gave a one-semester course on differential equation, which was the capstone of his 6-semester series of lectures on theoretical physics. We had a much harder time learning theoretical physics because it took us 6 semesters to get through classical physics, and by the end of that we hadn't heard a thing about quantum theory. Schrödinger's papers, as you know, solved the hydrogen atom. He then proceeded to apply perturbation theory to get the Stark effect. It was my task to present his perturbation theory to the seminar, which sounded perfectly straightforward, and I have used perturbation theory ever since, whether it was applicable or not. There was also an American postdoc, whose name I have forgotten, who asked my help in understanding the German of Schrödinger's paper. But it turned out that he needed much more help in understanding the physics than in understanding the German. And so I gave really 2 talks in that seminar. Sommerfeld's place was very useful also in other ways. I met many good graduate students, some of whom became very well known, like Peierls and Teller, or Unselt, who became one of the important astrophysicists in Germany. There were always large numbers of American postdoc visitors, and they were even more interesting. There was, for instance, Rabi and Condon, Robertson, Van Vleck, and later a man by the name of Lloyd Smith, whom you probably have not heard about, but who was very important for me later on, because he got me later on my job at Cornell University in 1935 when I was a refugee from Germany. Rabi and Condon in particular were often very much perturbed because Peierls and I were constantly talking to each other and giggling. And they thought that we were laughing at them, which we were not. From Sommerfeld I learned to solve problems exactly. I learned mathematical physics. I learned differential equations, which suited me very well. Much later, from Fermi, I learned how to look at a problem in a simple way and see the solution in a few minutes and then sit down and actually solve it. Schrödinger theory was not very well founded and seemingly had no connection with the early theory, either quantum or classical mechanics. But it was eminently successful. On the other hand, it had been preceded by some papers by Heisenberg, some in collaboration with Born and Jordan. Heisenberg's theory was based on the old quantum theory and made it viable, I might say. Quantum theory in the years from 22 on was trying to develop a method to calculate the intensity of spectral lines, and they decided one thing to do was to take the coordinate and expand it in Fourier series in terms of the fundamental frequencies of the system to be considered, q sub n times e to the minus I n omega t. And then the problem was to determine q sub n. The old quantum theory was hopelessly unsuccessful about this. So Heisenberg, in the summer of 1925, said one really shouldn't talk about the harmonics of a frequency omega, but one should talk of the frequencies which actually exist in an atom, and those, as we all know, are differences of the energy levels of the atom. So that he replaced this by a sum over a double sum over energy levels k and n, e to the minus I times the frequency in going from level k to level n times t, and of course omega kn is ek minus en over h. And he said, well, one should make a similar expansion for the momentum, and he would know what the coefficient should be for the momentum, namely minus I omega qkn, and we'll call that pkn with the same exponential. An m belongs here to the mass. So he said we should only talk about experimentally observable quantities, both the frequencies and these amplitudes, but should forget about the motion of electrons in orbits. Then he discussed just how these quantities q and pkn should occur in the theory. How would you form kinetic and potential energy from them? And he found that these quantities obeyed very strange multiplication rules which he had never seen before. But he wrote down these multiplication rules. P and Q just did not behave like ordinary algebraic quantities. When he came home to Göttingen, where the senior theorist was born, Max Born told him, but Heisenberg, what you have there is simply the multiplication of matrices. Now you all learn about matrices probably in your freshman year or at most in your sophomore year, but Heisenberg had never heard about matrices. So then Born and Jordan made his theory respectable from the mathematical point of view. However, this matrix algebra was very complicated, and you could solve only the simplest problems, like the oscillator and angular momentum. These two problems can still be better solved with matrix mechanics than with Schrödinger wave mechanics. But of course, with Sommerfeld, we did it all with waves. Now, so Heisenberg had a very clear connection with classical mechanics and the old quantum theory. His theory seemed well-founded. It seemed to be correct. But for instance, to get even the hydrogen atom took extreme mathematical skill. It was solved by Pauli in a paper which appeared at the same time as the first paper of Schrödinger. But nobody of less skill than Pauli could have used it at that time. So Sommerfeld said, we believe in Heisenberg, but we calculate with Schrödinger. And you will see in a few minutes that Heisenberg himself adopted this maxim very soon. Schrödinger may very well have been motivated partly by the Heisenberg matrix theory. There is a legend, I'm not sure whether it is correct, that the Bay, who was at the same university as Schrödinger at the time, namely Zurich, told Schrödinger, now look here, there is the matrix mechanics of Heisenberg, and I know that matrices are somehow related to differential equations. Why don't you find the differential equation which corresponds to Heisenberg's theory? Another source of Schrödinger's theory was de Broglie's waves. Everybody made fun of de Broglie's waves, which were published in 1924. Heisenberg got annoyed by that. Schrödinger got annoyed by that, and I understand, and this on good authority, that one winter while skiing, I suppose it was the winter 24 to 25, Schrödinger said, well, I'll show you. I will make de Broglie's waves respectable. And so he did. Schrödinger wanted his waves to be interpreted literally. He wanted the absolute square of the wave function to be the density of electrons. He was thinking of an electron smeared out, let's take the hydrogen atom, smeared out over space in the way the wave function indicated. But his own equation for the many-body atom, let's say for the lead atom, showed that this was impossible, because the lead atom with 82 electrons would have a Schrödinger equation in 3 times 82 coordinates in configuration space, and clearly you can't speak very well as an actual density of electrons in 246-dimensional space. It makes no sense. Not enough with that, the final decisive point was scattering. The Schrödinger equation must describe not only stationary states, but also scattering. This problem was solved by Max Born in 1927. And Max Born pointed out, together with his theory, that in a scattering experiment, you can detect single particles, electrons, protons, what have you. So it could not possibly be true that psi absolute square determines the density of the electron, because when you put in the detector, you would also always detect a single electron, which goes either into this counter or into that counter or into that counter, but never part of it into this and part of it into that. So therefore, Born proposed in his important paper in 1927 the statistical interpretation of the Schrödinger theory. And this statistical interpretation is what we now accept and use and teach in all our courses. Born's paper was a great paper. It's the basis for all collision theory which followed. And practically everything we do nowadays in nuclear physics, high energy physics, you name it, is a scattering problem. The problem which he solved was a problem which had been insoluble in the old quantum theory. Nobody knew how to deal with the with aperiodic phenomena with anything but stationary states. You could treat collisions classically, but there was no way of putting the old quantum theory into it. A further point in interpretation was equally important. This was Heisenberg's uncertainty principle. The uncertainty principle, of course, is familiar to you, and is usually written that the product of the uncertainty of momentum and of position is always greater than or equal to h bar over 2. This was, as most of you will know, essential for the reconciliation of the particle picture and the wave picture. A particle has an orbit where the position is given as a function of time, and in the old quantum theory, people assumed that there was an orbit for an electron in the atom. This was untenable, incompatible with the quantum condition. It was the uncertainty principle which smeared out these orbits sufficiently so that you could tolerate the quantum condition at the same time as you had the motion of particles. The complete, well, of course, the wave picture, as I said before, should not be taken too seriously either. The Heisenberg uncertainty principle is based on representing the particle by a wave. But the wave picture should also not be taken too seriously. There we have Born's statistical interpretation. After all, we do measure single particles, full particles, and not fractions. The complete reconciliation of the wave and particle picture was accomplished finally by the second quantization, the first example of which was given by Dirac, I think also in 1927, when he quantized the electromagnetic field and solved the eternal previous puzzle of the duality between light waves and light quanta. Before that, in the years of the old quantum theory, Eddington's statement applied, namely that on Monday, Wednesday, and Friday we believe in the quantum picture, and on Tuesday, Thursday, and Saturday in the wave picture of the electromagnetic field, and on Sunday we pray that there be some solution to this puzzle. Well, where was I in all this development? I did not contribute to either of these, to any of these fundamental interpretations of quantum mechanics. I was involved with the theory of an experiment by Davison and Görmer, which you may know about, in which they established, I think in 1926, that the de Broglie waves were real for the electron, that indeed electrons which interacted with some crystal were reflected as if they were waves, as if they were X-rays. There were maxima, diffraction spots, like the Laureate spots from X-ray diffraction, and you could deduce from these spots the wavelength of the electrons, and indeed the wavelength came out to be h over mv as predicted. However, it didn't quite fit. The wavelengths, which the spots were not at exactly the right point. They occurred at somewhat the wrong energies. And Sommerfeld asked me for a thesis to look at this. And I found out fairly quickly that you could explain the Davis-Germer experiments by assuming that in a metal the electrons were subjected to a potential energy of about minus 20 electron volts. If you assume that, this attraction into the metal, you could explain the observed electron diffraction experiments. Now the question then arose, what was this connected with? How does this relate to the observed work function of metals, which is generally of the order of 5 electron volts? And that was very soon cleared up. Namely, electrons in metals are essentially free. I'll come back to that in a few minutes. And obey Fermi statistics. So you have a certain Fermi energy. If you calculate the Fermi energy from the electron density, it's about 15 eV, and so that explains the difference. Then, having done this, I was to develop a complete theory of the scattering of electrons by crystals, which I did as a thesis. Unfortunately, I tried to do too much. The interaction of electrons with metal ions is very strong, and I had no method to treat it except perturbation theory, as I told you earlier. And perturbation theory is not applicable in this case. So I got a first approximation giving the scattering, telling also about interference between two scattered waves and all that, all of which I modeled after a theory of X-ray diffraction, dynamic theory of X-ray diffraction, which was due to Ewald, who afterwards became my father-in-law. So this part was all right, and another part was still all right, namely I found out that the form factor for electron scattering is the charge of the nucleus minus the form factor of the atom, of the electrons in the atom, which depends on the momentum change during the scattering. This is a useful result, but I didn't emphasize it at all. So Pauli was quite right when he first saw me, which was a few months after I took my PhD. First thing he told me was, Mr. Bethe, I was very disappointed in your thesis. A little later, in 1930, 2 years later, I continued the scattering theory which had been started by Born. I saw that certain things could be simplified in actually using that theory. In that theory, in the first Born approximation, you encounter an integral which goes as follows. if number 1 is the particle which is being scattered, then you have the incident wave function of the scattered particle multiplied by the complex conjugate of the final wave function, and let me call that R1, integrated over the volume of particle 1 times the interaction 1 over R12 times the final and the initial wave function of particle number 2. Psi initial of R1. This is inelastic scattering going from an initial to a final state for that particle and having a change of momentum of the scattered particle. This, of course, refers to the electron in the atom. Now, I made the mathematical discovery that this integral can be transformed, and I'm sure mathematicians had known that for at least a century, in the following way: by first integrating over R1 and then over R2, 4 pi over q squared. Q is this difference, the momentum change, times an integral psi final star psi initial times e to the I q dot R2, integrated only over the atomic electron. Well, this also, of course, is now presented in every course, but it was very useful because, of course, this is eminently simpler. You have to do only one integral instead of having to deal with 2 variables at first and integrating twice. And so everything became very simple, and it was possible to calculate electron scattering, elastic as well as inelastic, from the hydrogen atom and from more complicated atoms. It became further possible to sum this absolute square of that, giving the cross-section, to get the total cross-section summed over all final states of the atom, to get, and especially to get the expected energy loss of a particle, which is the difference in energy, that is the energy transferred to the atom, multiplied by the differential cross-section, which is the absolute square of this. And that could be nicely summed by means of a sum rule. And so I could calculate the energy lost by a charged particle when going through matter. Well, that seemed to be nice, but I didn't realize that it was important until I came to Cambridge, England, when Professor Blackett, later Lord Blackett, told me, well, that's very important for all of nuclear physics. Please calculate for us the relation between energy and range of a particle. Well, I proceeded to do so, and to my great surprise, it agreed with experiment. It has been used, it was used first for those old experiments. Nowadays it is mostly used in particle experiments where you determine the momentum of a particle from the curvature in the magnetic field and then the velocity from the energy loss, that is from the number of ions that the particle forms per centimeter path. So this was very satisfactory. As a matter of fact, I consider this my best paper. The world does not. In the meantime, atomic physics was marching on. Clearly, Once you had done the hydrogen atom, you wanted to do the next atom, namely the helium atom. Many physicists, including Bohr himself and Heisenberg, had tried to solve the helium atom on the basis of the old quantum theory. They failed completely. They could get any number of different results for the binding energy of the helium atom, none of which agreed with experiment. Heisenberg, who had an investment in the helium atom, proceeded to solve it in wave mechanics and did what Sommerfeld had recommended. We believe in Heisenberg, but we calculate with Schrödinger. So he succeeded. And what did he accomplish? This was also, I believe, still in 1927. First, he got close to the binding energy. This was later improved by using the Schrödinger variational method, by Hilleros, and later by many other people. The best calculations have been done by an Israeli Pekaris, and he gets the non-relativistic energy of the helium atom to an accuracy of 1 part in 10 to the 12th. Of course, that's relative to the binding energy of the hydrogen atom. But it also agrees with experiment, by the way. Heisenberg, secondly, explained the long-standing puzzle that helium seemed to have two spectra, orthohelium and parahelium. And the only spectral lines you observe correspond to transitions within orthohelium or within parahelium. In the old days, people thought that maybe there were two really distinct gases. Heisenberg showed, and you all know that these two spectra come about because the wave function can be either symmetric or antisymmetric in the spatial coordinates of the two electrons of the helium atom. Third, he got the connection with spin. He postulated that the total wave function must be antisymmetric. Dirac had found that independently, and that was Dirac's basis of the Fermi statistics. If the total wave function is antisymmetric, then the antisymmetric spatial wave function goes with a spin of 1, parallel spin of the two electrons, and gives you triplet states, and the other one gives you singlet states with total spin 0. This was not so easy to say in those days because spectroscopy was incapable in those days to resolve the triplet states. They could only show, the spectroscopists could only show a doublet. And it was later on found that indeed two of the states are very close together, and nowadays you can resolve them by modern methods, modern spectroscopic methods, and you can do a theory doing the calculating the splitting in detail. Heisenberg's calculation of helium opened the way in two directions, namely to treat molecules and to treat complex atoms. The hydrogen molecule, the simplest of all molecules, was solved by Heitler in London, and they showed that it is important to have the two spins of the two electrons in opposite direction, just as they are in the ground state of the helium atom. So you have a saturation of spins. This theory gave a theoretical foundation to some ideas which Lewis, a great chemist, had previously about the chemical bond. This was the theory of the homopolar chemical bond, and it, in the hands of Pauling and many other chemists, it was developed into a real understanding of chemistry. It is the foundation of perhaps the most important part of theoretical chemistry. This understanding of chemistry was further extended to the solid state, especially to metals, whose binding is again different from both the ionic bond and the homopolar bond in chemistry. The first step, as so often, was taken by Pauli, who said that the electrons in a metal might be free, but then would obey Fermi statistics. I mentioned that before in connection with the work function. Sommerfeld took this up and developed a complete theory of free electrons and showed that free electrons obeying Fermi statistics would solve all the puzzles of the old electron theory of metals, which had been invented 20 years earlier by Drude and never gave the right answers. He could calculate conductivity, the ratio of thermal to electric conductivity, and all sorts of thermoelectric and magnetoelectric effects which nobody had understood before. But he did not explain why the electrons could move freely in the metal. After all, there were ions in the metal which exert very strong forces on the electron. How could the electrons go through that lattice without paying any attention to it? This was solved in 1929 by Felix Bloch in his thesis. He showed that the periodic structure of the metal made it possible for electrons to move freely and to move without any resistance. In fact, I'm told that Bloch got that result very quickly in his thesis and went to Heisenberg and said, "This is an elementary answer I got that can't be very interesting." And Heisenberg said, "But you have solved the main problem." And then the rest was more calculation. This doesn't explain why liquid metals also are good conductors, but Vicky Weisskopf's theory of liquids makes us understand that liquids, at least at relatively low temperature, do behave quite a lot like solids, and therefore this becomes explainable. The quantitative theory of electrons in metals was started by Wigner and Seitz a couple of years later, and it fell to me to write an article in the Handbuch der Physik on the theory of metals. It was written together with Sommerfeld. Sommerfeld was the man who was asked by the editors to write this. Sommerfeld said, "Well, I'll write it if Bethe does 90% of the work and takes 90% of the honorarium." That was fine with me, especially the latter, which became, it was quite a good honorarium. And so when I had to emigrate from Germany, I had at least a little bit of money to fall back on. The other theoretical area opened by Heisenberg's paper was that of complex atoms. How do you explain, let's say, the spectrum of the silicon atom? There are multiplets which the spectroscopists had found much before, But already calculating the lithium atom, which Heisenberg still did, you got extremely complicated wave functions. The solution to this was found by Wigner and von Neumann, and the solution was in terms of group theory, which at least enabled you to understand the multiplets and to calculate which multiplet would lie lowest in energy. It confirmed Hund's rule, namely that the highest multiplicity always lies lowest. But it was an extremely complicated theory. I wanted to understand complex atoms. The quantitative side always interested me. So I learned group theory. And then there had to be something to apply group theory to. So I did a paper on the group theory of atoms in the somewhat unsymmetric fields which an atom is exposed to in a crystal. And I found that the energy levels would be split into several levels, and since then people have found that this is useful and that indeed it does apply to the behavior of atoms in a crystal. The group theory was not needed for the free atom. Slater, whom many of you remember as a professor of theoretical physics at this institution, did it the correct way in 1930. He showed that all you need to know is that the total wave function is antisymmetric, and so he wrote down what is known as a Slater determinant, putting all the wave functions in a row and all the electrons in a column, and everybody now uses the Slater method to treat the complex atoms. The quantitative calculation of atoms required still a different approach, and this was suggested by Hartree and Fock. Hartree did many of his numerical calculations on the Bush analyzer, which also had its home here at MIT. To solve the Hartree-Fock equation for an atom is extremely difficult, and Hartree's methods were quite insufficient. In fact, even modern computers are generally insufficient, as was found by the atomic theory group at Los Alamos Scientific Laboratory. The calculation is unstable, and therefore it is necessary to first use an approximate method. That again was invented by Slater and then improved by Cohn and Sham. And once you have the approximate solution, then you can do the accurate calculation. The Hartree-Fock method, as you will know, treats all electrons in the field of the general field of the atom. It doesn't treat the interaction of the electrons except in an overall way. This was solved only in the 1960s, especially by Nesbet at the IBM research laboratory in San Jose, California. And he can calculate the ionization potential of an atom to an accuracy of about 0.03 electron volts out of some 10 or 20 electron volts, which is an exceedingly good result of the theory. It is so good that you can now predict the energy levels of atoms you have never seen, and especially of ions you have never seen, which is useful for guiding spectroscopists. An important part of this, of course, was the spin. This was discovered in 1926 by Goudsmit and Uhlenbeck. There was a celebration in the American Physical Society in 1976. It was foreshadowed by the Pauli principle, which was published in 1924, in which Pauli found out that it was necessary to assume that always two electrons could occupy one orbit. This was putting some theory behind Bohr's previous explanation of the periodic system. You had to explain why two electrons could sit in one orbit. Of course, Pauli couldn't, but Gauss-Schmidt and Uhlenbeck could. Even though Pauli had discovered this two-electron business, he very much discouraged Kronig, who had previously had the idea of the spin, and Pauli looked at Kronig's idea and said that is nonsense, and Kronig never published his paper. Pauli, however, atoned for this by inventing the quantum mechanical equation which includes spin, in which he invented the spin matrices, which you now all use, and which of course are useful for many other purposes also, such as isotopic spin. Well, I think I have given you enough of a picture so you can understand that we were convinced back in those late 20s that every problem in physics can be solved. At least every problem which involves non-relativistic quantum mechanics. And this is the feeling which Vicky Weisskopf talked about in his introduction. You shouldn't think that theoretical physics is now uninteresting. It is as interesting as ever. One of the differences in the physics then and the physics now is that at that time we had a tremendous backlog of experimental information from spectroscopy, from scattering experiments, which nobody had been able to explain. And so theory was exceedingly successful in the space of some 5 years to explain essentially all the accumulated information. We were also very lucky that we had an equation which really worked, the Schrödinger equation, with the Pauli spin addition. It was a very exhilarating time, and it made all of us of our generation great optimists about physics, namely that problems can be solved. And this part of our conviction, I think I want to impart to you, and I think you should believe it today also in the much more difficult problems of particle physics and similar problems. Unfortunately, most of the simple problems we solved in those years, and I apologize for taking them away from you. One problem we didn't solve in those days, and that was superconductivity. Everybody was convinced that it was a problem of non-relativistic quantum mechanics. But it was solved only in the 1950s by Bardeen, Cooper, and Schriefer. It was shown that indeed it was a problem of non-relativistic quantum mechanics, so it was soluble, but it took a long time. And so also in your work you should not be too disappointed if it takes a long time. Finally, in conclusion, relativity theory, of course, had to be combined with quantum theory. This also was still done in the 20s by Dirac in the Dirac equation, 1928, which gave the spin automatically. And in the meantime, of course, we know that even the Schrödinger-Klein-Gordon equation, on which Vicky Weisskopf worked a little later, also has its place in physics, because it explains the behavior of particles of zero spin, of which we have a fair number. The Dirac equation explained the hydrogen atom, later the helium fine structure, gave the spin automatically, gave the G factor of the spin, and therefore the anomalous Zeeman effect. It predicted the positron, but Dirac did not have the courage to make this prediction. He thought he had an equation for the proton. It also predicted thereby that particles can be created and annihilated, which is the bread and butter of today's physics and has remained so. Well, I hope to have given you some picture of what we were interested in the late 1920s, what a wonderful time it was, how quantum mechanics not so much was born but developed in a very short way to explain the known facts of physics. In fact, one might say that it explained most of the physics that you see in everyday life, and of course all the chemistry, and we expect the biochemistry and so on. But physics remains always new. There are always new problems, and so I wish you the best of luck in solving those. Thank you.
Hans Bethe consented in having a little question period, but I would like before that tell you that if you think that this is all Hans Bethe did, you're wrong. He didn't talk about his tremendous and fundamental part in nuclear structure, in explaining why the sun is hot when it shines, and he didn't tell his tremendous contribution to field theory and quantum electrodynamics and so many other things. So this is only a small, small part of what Hans Bethe gave to physics. Questions?
Okay. I was wondering, in the period of 1924 to 1929, what were the experimentalists doing?
Nuclear physics. You mean 34 to 39 or 24 to 29? 24 to 29, well, there were quite a number of experiments in spectroscopy. A large number on, for instance, in the place where I worked in Munich, the great thing was canal rays, that is to get protons or other, or other atoms, ions, separated into a tube and then do experiments on them to find out, for instance, the lifetimes of atomic states. And people did a lot of experiments on the diffraction of particles, of electrons, most of them right, one set of them quite wrong. They did hyperfine structure measurements, that is, people began to be interested in the behavior of the nucleus, where there was lots to do.
Radioactivity.
And radioactivity, indeed.
But the set of experiments you're talking about were done before.
These were done before.
Question?
Yeah, you mentioned before about Fermi and how Fermi, in your interaction with Fermi, he taught you how to look at a problem and solve it very quickly and then go back and work through the solution. I wonder if you had a story or two about Fermi to illustrate that.
Well, one feature of my cooperation with Fermi was when we were both interested in quantum electrodynamics. There had been 3 separate formulations of the interaction of electrons between 2 electrons. One was that by Heisenberg and Pauli, which was made more palatable by Fermi himself in his article in the Reviews of Modern Physics, which people can read quite easily, in which the field was quantized and everything was done beautifully and in detail. The second was a proposal by Möller of Denmark, in which he said, well, let's represent an electron by an initial and final state, both having wave functions. So let's take the transition density, psi initial times psi final star, and consider this a source of the electromagnetic field. You then calculate the scalar potential and the vector potential, which you can do in a perfectly relativistic way. And this was and then you can let that act on the second electron. Third was the theory by Bright of the interaction of 2 electrons in the approximation v square over c square, so not fully relativistic. Fermi and I sat together for a day or 2 in order to find out how these are related, and he saw immediately how to do this. And then on the 3rd day he said, well, now let's write the paper. So he went to the typewriter. There were no secretaries at the institute in Rome. He went to the typewriter and said what he was going to write, and occasionally I would criticize that. And whenever we wanted to write an equation, I would write this equation by longhand. And on the 3rd day, in fact, fraction of the 3rd day, the paper was written and then published in Zeitschrift für Physik. So this was one of the examples of our collaboration. The other was that when anybody had any problem in the lab at Rome, they would come to Fermi, and particularly when 2 of the younger people disagreed, they would refer their disagreement to the Pope. Fermi was called the Pope, and the Pope would then sit down and say, well, now let's look at it this way. And in something like 20 minutes, he would have all of it cleared up and made the fundamental physics clear, and then people could go ahead and do the explicit work.
What was the Max Planck awardee?
I have no idea. I never met Max Planck. I knew he was a great man. I don't even know how he reacted to quantum mechanics, either Heisenberg's or Schrödinger's. Do you, Vicky?
Yeah, no, I think he was sympathetically inclined. Let me tell you an anecdote here, if I may. Maybe. The anecdote is this, that I was in Berlin at that time. It must have been in the late 20s, and there was a seminar by Hans Kopfermann, who is an experimental physicist, by the way, and who at that time did spectroscopic studies of age, the different ways of determining Planck's constant by the photo effect, by spectroscopic, and so on. He had a whole series of maybe 8 or 10 different ways and always got the same value. And in the first row of the seminar were sitting Einstein, Planck, and Nernst, and a lot of other famous people. And I overheard Nernst. Nernst asked a few questions to Kopfermann. I don't understand, how could you measure this so accurately? And Kopfermann explained it. And then Nernst said to Planck, well, Herr Kollege, I say it in German and then in English. Well, Herr Kollege, dann haben Sie ja noch einige Chancen. Then you have still a few chances of being... So, no, I think Planck was very sympathetic to modern quantum mechanics. He did not work in it. He was, after all, I don't know how old he was at that time, but in the 70s, and I know then you can't work anymore. And but in contrast to Nernst and to other people of his age, he was very sympathetic to quantum mechanics. Another question? Whether you worked with Einstein?
I have never worked with Einstein, except politically. I met him only in this country, in Princeton, and I never discussed physics with him. He worked at that time on the unified field theory. He was a great opponent of Bohr's interpretation of quantum mechanics, as you may know, and this, I think, was one of the few occasions in which Einstein was quite wrong. Hitler came to power in 1933. I was half Jewish, I still am. And that meant that I could not get any position at any university in Germany. And since I wanted to do pure physics work, I couldn't stay in Germany. So it was as simple as that. Also, I didn't like him very much. Some of you may have seen yesterday's New York Times. It has in the book review section a review of some books which try to rehabilitate Hitler and say that he was not such a bad man. The reviewer agreed with me. He was as bad a man as you ever would want to see.
You said that at some point you realized that all the phenomena in one's everyday experience could be explained by the non-relativistic quantum mechanics. And I sort of envisioned some small group of physicists, I guess who must have been an elite actually at the time, who understood this and sort of could see all of immediate experience becoming apparent. Did you feel lonely? I mean, did you sort of want to tell the world? Your friends who your very best friends who just happen to not be physicists, I mean, were you sort of busting to tell them, or was the feeling?
Well, of course we wanted to tell, and I guess it was told to a quite considerable extent. The feeling of understanding certainly was transmitted to the chemists, and very well transmitted to them. They made use of quantum mechanics as much as the physicists did. Of course, explaining the world is to to be understood the same way as Laplace understood it back 150 years earlier. Namely, if you can solve all the mathematics, then you might explain any phenomenon that you choose to. But even today's computers are by far insufficient to solve all the mathematics. I mentioned that even the Hartree-Fock equation for an atom is quite difficult to solve. I don't believe that I, at least, and most of the physicists that I knew, had any intention to tell it to the world at large. One of the results, namely the Heisenberg uncertainty principle, became very famous and was taken up by philosophers, and I think is fairly generally known, if not understood. But certainly we never thought we could solve the human problems that people have, and I still believe firmly that the human problems are on a different plane and cannot be solved by solving the Schrödinger equation.
I think we should now really thank Hans Bethe for this unusual, unique experience of listening to him. Thank you.